Hello students, this is the third video for the chapter Solutions. In the previous video, we already had discussed the concept about solubility and the factors which affect it. In detail, we considered each type of solutions and we also discussed the importance of Henry's law and its applications. Hope it was clear for all of you. Now we'll begin on with this session of the video. Today we will be discussing about the vapor pressure of a binary solution. When we talk about binary solution, we know that a solution which consists of a single solute and a single solvent constitutes a binary solution. In this category, we do have three clauses to be discussed. Gas in a liquid solvent, liquid in a liquid solvent, and the third one is solid in liquid solvent. The third category we will be discussing later. Regarding the first category, gas in liquid, we have discussed in our previous video, and in that topic we discussed about Henry's law. In this session, we shall be broadly discussing on the concept of liquid in a liquid solvent. When we consider liquid in liquid solvent, we will be discussing about Raoult's law. Let's proceed on to our concept of liquid in liquid solution. When we consider a liquid in liquid solution, we will be keeping in mind that the liquids which is acting as the solute and the liquid which is acting as the solvent, both will be miscible, yet both will be volatile in nature. So in short, we can say that we will be discussing about a solution of liquid in liquid where both of them are in volatile nature. When we consider in this liquid, you can see in the image, we have got three jars there. In the first jar, you can see that we have got a component A, which is liquid, and you can see there that that liquid is having its vapor. Then you have got the second jar. In the second jar also, you can see that there is the liquid component and its vapor is present in the jar. So, in these two jars, you can see that they are in their pure state and the vapors will give you the pressure in their pure state. Now, in the third jar, you can see that we are having a mix of the two components A and B. At the same time, you can see that the vapors of both the components are present there. It means that these two components are miscible, but yet they are volatile. Now, while seeing on to this figure, you can easily see that the number of the particles which comes into the vapor state depends upon the total concentration of the components which is present there. So, in short, we can say that when a mixture of two miscible liquids is considered, both being volatile, then the partial pressures of the gas is directly proportional to their mole fraction. The mole fraction can either be in the solution or in the vapor state. Now, here you can see the picture of a scientist. Do you recognize him? Yes, he is a French chemist named as F.M. Raoult. Raoult was the scientist who actually gave a mathematical relation between the vapor pressures of the components of the volatile liquid solution and the mole fraction. This law or this relation is called as Raoult's law, and it states that for a solution of two volatile liquids, the partial pressure of each component is the solution is directly proportional to its mole fraction. Now let's see the mathematical way of its expression. Let the partial pressure of the component A be PA and the partial pressure of the component B be PB. Then we can have the expression according to Raoult's law as PA directly proportional to chi A and PB directly proportional to chi B, where chi A and chi B are the mole fractions of the components A and B in the solution. Now, changing the proportionality constant, we will get PA is equal to PA0 chi A, and for PB is equal to PB0 chi B, where the PA0 and PB0 are the vapor pressures of the pure component state. That is, when you consider the liquids in their pure state, they will be giving a pressure of PA0 and PB0. The small letter PA and the small letter PB gives the partial pressure of the gases once they are mixed together. Now, I hope that you remember the Dalton's law of partial pressure which you learnt in your 11th standard. It had stated that when two gases are mixed together which are not interacting at a given temperature and volume, then this total pressure is equal to the sum of the partial pressures of the components present. According to this law, we can have P total is equal to PA plus PB. Substituting and applying the Raoult's law into it, finally we will be getting the following equation as PA0 minus PB0 into chi A plus PB0. This is the modified equation or the applied equation to the mixture of the volatile liquid components. Raoult's law can also be explained on the basis of graphical representation. Now you can see here that the extreme left side, you can see that we have got the y-axis with vapor pressure and the x-axis is given by mole fraction. Though I have marked it as mole fraction, you can see here that I have considered only a single component there. Chi A is equal to 0 and it extends to chi A is equal to 1. Now, according to Raoult's law, as we mentioned, that the vapor pressure is directly proportional to the mole fraction. So, as mole fraction increases, the vapor pressure also increases. But since we consider only a single pure component here, you can see here that the graph can be later extended to meet a particular point on the axis where the right side of the axis is again marked as vapor pressure. This point where the axis meets, you can see here that it has attained the maximum of the pressure. So, that will be the pressure exhibited by the pure liquid when there is only one single component and it is marked as PA0. The graph line can be marked as on the basis of Raoult's law. PA is equal to PA0 chi A. Now, I am going to introduce the second component, that is the B component. Now, when we introduce the B component, the change that you can see on the bottom mole fraction axis is that where chi A is considered as 1, now the second component has to be marked 0 because we are having the fraction of component. So, in this case, the extreme right side will have chi B is equal to 1. Now, on the marking of this graph, you can see that sometimes it is also marked as chi A is equal to 1 or chi A is equal to 100%. That's only the way it is represented. Now, coming on to the graph, Let's consider the graph for the second component alone. So the graph will be like this. You can see the blue line here, it shows the Raoult's law effect onto the second component. So you can see here that at the extreme left side, PB0 marks the vapor pressure of the pure component B. Now we are considering a solution of these two volatile miscible liquids. Then the total pressure can be marked as given here. You can see that a red line shows the total pressure of that particular solution, which is given as P total is equal to PA plus PB. So this is how the graphical representation is being explained. As previously I mentioned that the mole fraction can be considered both in the solution and in the vapor phase. Now I will show you how we will be calculating the same way of partial pressure in terms of vapor pressure in the vapor state. Now you can see here the jar which I had shown previously, which consists of the two miscible volatile liquids. Chi A and Chi B representing the mole fraction in the solution state, and YB star and YA star representing the mole fraction in the vapor state. Now, vapor pressure of miscible volatile components can be calculated using the following formula. You'll get the equation as partial pressure of A component is equal to YA star into P total, where actually P total is the proportionality constant change. Similarly, we can write it for PB also. PB, partial pressure of B component, is equal to YB star into P total. Here, YA star and YB star are the mole fractions of the components in their vapor state. So you have got net of two types of expressions where the mole fractions are considered separately, one in the solution phase and one in the vapor phase. In the solution phase, we write it as PA is equal to PA0 into Chi A. In the vapor state, we'll consider it as PA is equal to PA total into YA star. Now let's do a problem based on this. The problem is there on the board for you. The vapor pressure of pure liquids A and B are 450 and 700 millimeters of mercury respectively at 350 Kelvin. Find out the composition of the liquid mixture if total vapor pressure is 600 millimeters of mercury. Also, find the compositions of the vapor phase. When we come across a problem, we are supposed to first jot down the given datas. Here the given datas are the partial pressure of the pure liquid PA0 is equal to 450 millimeters of mercury, and for PB0 is 700 millimeters of mercury. P total is also given as 600 millimeters of mercury. Now using the equation, P total is equal to PA0 plus PB0 minus PA0 into Chi B, we can easily calculate the mole fraction of the component B. On substitution, the final answer comes out as Chi B is equal to 0.6, and by substituting into the equation 1 minus Chi B is equal to Chi A, you will get the answer as 0.4. Now these are the mole fractions in the solution phase. Now we will go on to the calculation of the partial pressures of the respective components. Using the equation, Raoult's law equation, PA is equal to PA0 into Chi A for A component and PB is equal to PB0 into Chi B for B component. And on substitution of the values which we previously discussed, we get the values of partial pressure of A component as 180 millimeters of mercury and the partial pressure of B component as 420 millimeters of mercury. Now we'll again use the equation in terms of the mole fractions in vapor phase as PA is equal to YA star P total, PB is equal to YB star into P total. Using this equation, we will be getting the mole fractions in the vapor state as
YA star is equal to 0.3 and YB star is equal to 0.7.
Now, based on the concepts of the Raoult's law, later on, the solutions has been classified into two categories. Let's go into its detail. The two categories of types of solutions are ideal solution and non-ideal solution. The non-ideal solution is further divided into two sections. The one which show positive deviation and the second one is the ones which show negative deviation. Let's study about them in detail. Ideal solution. What do we mean by an ideal solution? An ideal solution is that solution which obeys the Raoult's law under all conditions of temperature and concentration. The conditions which are satisfied for an ideal solutions are delta V mixing is equal to 0 and delta H mixing is equal to 0. That means when we mix together two solutions which are volatile in nature and which are going to obey the Raoult's law, when we mix these two solutions, there will be no change in the volume of the net solution. That is why we say delta V mixing is equal to 0. Similarly, there will not be any change in the enthalpy also. So, delta H mixing is equal to 0. Now, coming on to the concept of the molecular level of interactions, we can see here that the nature of interaction between the component molecules AA and the component molecules BB will be the same after the mixing of the two components. That is, the interaction between AB will also be the same as their previous ones. So that means that we have got in total of three conditions to be satisfied for the solution to be called as an ideal solution. First one, delta V mixing is equal to 0, delta H mixing is equal to 0. And then we have got the condition that the AA interaction, BB interaction is equal to the AB intermolecular interactions. So, all solutions obeying Raoult's law are considered as ideal solution. Now, a few examples of such solutions which are given here are benzene and toluene, N-hexane and F-heptane, ethyl bromide and ethyl chloride. These are only few examples mentioned here. We have got more than these. Now, let's talk about what is a non-ideal solution. Of course, it's easy to say that a non-ideal solution is those solutions which do not obey Raoult's law. That is practically correct. Now, why they do not obey Raoult's law is because in this category of solutions, the intermolecular interactions is not as we expect, or they have got a phenomenal change. Now, let's try to understand each category of a non-ideal solution. The very first one is given here, positive deviation. When we say that we have got a positive deviation non-ideal solution, we mean that the graphical representation from a non-ideal solution is having a positive deviation. That means that the vapor pressures of individual components as well as the vapor pressure of the total solution has increased. You can see here in the graph, the yellow dotted line shows the ideal condition and the red line shows a positive deviation. Now, let's check on to the conditions which is being satisfied by a positive deviation non-ideal solution. You can see here the conditions are that P total is greater than PA plus PB, where PA and PB is considered the sum for an ideal solution. Similarly, the different conditions has been given here. A notable condition you can see here is that here the delta V mixing is greater than 0 and delta H mixing is also greater than 0. The increase is not very prominent, but yet there is a small amount of increase. Let's understand it further by using a particular example here. A good example of a positive deviation non-ideal solution is a solution of ethyl alcohol and acetone. You can see here that the two ethyl molecules which has been given here are having an interaction forming a hydrogen bonding, which you know that is a stronger bond than a van der Waals force of attraction. Similarly, we have got here acetone, which also is having an interaction. But when we mix them together, you can see here that the acetone molecule gets mixed up with the ethyl alcohol molecules, and the bond or interaction which is being formed there is found to be a very weak interaction. So that means that the AA component interaction and BB component interaction is stronger than the AB interaction. So from this you can easily conclude that because this interaction is stronger, the AB interaction is the AA interaction and BB interaction is stronger than the AB interaction, obviously the vapor pressure increases. Once again, I have just clarified the same concept here. Consider the solution of components ethanol and acetone. Ethanol has hydrogen bonding, whereas acetone is not having any special type of bonding. But when they are mixed together, the acetone molecules come in between the ethanol molecules, and this decrease, and there is a net decrease of intermolecular interaction, which further increases the vapor pressure. Few examples are given here: benzene and carbon tetrachloride, water ethyl alcohol, acetone ethyl alcohol, acetone and benzene. These are just few examples for positive deviation non-ideal solution. Now, we will move on to negative deviation. When we come to the concept of negative deviation, you can see here that again the graph shows it very clearly that there will be a decrease in the vapor pressure. You can see here the conditions which is written here. Now, why these conditions arise? It is because of the difference in their interaction behavior. Let's come to the detailing of this concept by taking an example. You can see here an example given: chloroform and an acetone solution. The chloroform molecule and the acetone molecules have got only a weak interaction between them. But when we are going to mix these two miscible volatile liquids, you can see here that there will be a special bonding arising between the acetone molecule and the chloroform molecule. The bond is being shown there, and that bond is the hydrogen bonding. So now it is very clear to all of us that AA interaction and BB interaction is weaker than AB interaction, and this definitely leads to the decrease in vapor pressure. I have explained it one more time. Now you can see here that how the hydrogen bonding is being formed. The hydrogen bonding formed here is between the carbonyl group C double bond O linkage of acetone and the hydrogen of the chloroform molecule. Various examples under this category is benzene and chloroform, water HCl, water and HNO3, acetone and aniline, and we have got many more examples also. Now, when we consider these solutions, whether it be a positive deviation non-ideal solution or a negative deviation non-ideal solution, we have come across a particular condition where the binary mixtures are having the same composition in the liquid and vapor phase and boil at a constant temperature. This condition solutions are called as azeotropic mixtures. That is, we can say that azeotropic mixtures are those mixtures which are having the same composition both in the liquid and the vapor phase and boil at a constant temperature. Now, this azeotropic mixture is also of two types. You can have minimum boiling azeotrope mixture and you can have a maximum boiling azeotrope mixture. Now let's discuss maximum boiling azeotrope. You can see here in the case of maximum boiling azeotrope, it is shown by those solutions which give negative deviation. Here an example is also given to you. Nitric acid and water is an example of a negative deviation solution which we have already previously seen. Now when these two solutes and the solvent, when these two liquids are mixed together, we come across a particular concentration condition. You can see here very clearly when 68% nitric acid is mixed with 32% of water by mass. That particular composition constitutes an azeotropic mixture. Now, since the example comes under the negative deviation category, we can say that negative deviation non-ideal solutions give maximum boiling azeotropes. Now, let's discuss about the minimum boiling azeotropes. In the case of minimum boiling azeotropes, those solutions which show positive deviations give such an azeotrope. You can see here an example, ethanol and water, which we discussed already. In the case of ethanol and water, it comes under a positive deviation non-ideal solution. Such a solution, when comes across a particular composition condition, it becomes an azeotrope mixture. You can see here that when we consider 95% by volume of ethanol, it becomes a minimum boiling azeotrope. That is all the contents present for this particular video. I hope that it was well clear for you. We have covered very important concepts like Raoult's law, the concept of ideal solutions, non-ideal solution, positive deviation, negative deviation, and finally we discussed about the azeotrope mixtures. In my next video, we shall be discussing the concept of colligative properties. Thank you for watching my video.